Okay, so how do we simplify rational expressions? And remember, we have to state restrictions, which gets even more important later this unit when we start solving equations involving this stuff. So if you recall, how do we simplify? So the first one, A, x squared minus 36 over x plus 6. I have to factor everything. If it wasn't simplified, I'd simplify first, then factor, and then I can see what divides. This is just like putting fractions in lowest terms, or multiplying fractions, dividing fractions, adding fractions, subtracting fractions. It's the exact same steps, but because we have all these x's and all these complicated expressions, it may not look like that. But if you look back at your notes from grade 11, if you have them, or if you look back at other grade 11 notes, you'll see that you probably start this looking at fractions and reminding yourself how they work. So the bottom is there's nothing I can do with it, but the top is factorable. It's the difference of squares. So x plus 6, x minus 6 over x plus 6. And so this is just like, as I said with fractions, if I had something like 8 over 4, and I turned it into 4 times 2 over 4, and then I divided the 4's together to give me 1. As long as everything is multiplied, I can do that, right? If it looked like this, 4 times 2 plus 1 over 4, I can't divide those 4's. But as long as everything is multiplied, I can do that. So the x plus 6 and the x plus 6 divide to 1, and I'm left with x minus 6. But what case would exist where I wouldn't be allowed to do that? I wouldn't be allowed to divide x plus 6 by x plus 6. If x was negative 6, why would I not be allowed to do that? Because then the x plus 6 part is 0, and you're dividing by 0. So what that means, and I hope you remember doing this in grade 11, or I hope you talked about it this way in grade 11, is that original expression, x squared minus 36 over x plus 6, simplifies to x minus 6 unless we started with x equaling negative 6. Because if that was true, our original expression had no value. If I sub negative 6 into the simplified version, I get negative 12. But that's not true, because if I sub it into the original equation, I get undefined. So this is not a simplified version of the original expression when x is negative 6. So we have to add that restriction. And when we start graphing these, like I said, it's going to become even more, or solving these, it becomes even more obvious why we have to do that. Kind of remember doing this? Okay. Let's take a look at the next one. So, what am I missing here? So what's going on with the printout? Something, because it's almost Halloween, something weird's going on. Okay, so I've got one big mess divided by another big mess. How do you divide fractions? You flip the one that you're dividing by and change it to multiply, right? So that part should be pretty simple. I'm going to do that, and I'm going to factor everything at the same time. So this mostly what you see is so far as simple trinomials, maybe complex. So what's this? X minus 7, x plus 4 over x plus 5 times, I'm going to factor the bottom, which is x plus 5 squared, and you can write it as squared or you can write it out. And then what do I have on top? X plus 4, x minus 2. Lots of factoring. So at this stage, I can divide things out where it works. So x plus 5 with one of the x plus 5s and x plus 4 with one of the x plus 4s. And I get x minus 7 times x plus 5 over x minus 2. So that's a simplified version, but it's going to have a lot of restrictions. Basically, at any point in time, if you were dividing by something that would be 0, it's a restriction. So you can either kind of make a list as you go, or you can wait till the end, and then you have to look back, but you don't just look at the final step, right? So x cannot equal positive 2, but it also can't equal negative 4. And I was also dividing by x plus 5 up here and x plus 5 up here, so it also can't equal negative 5. Anything else? That takes care of that. And those ones and that one, I think that's good. Right? So it's not just in the last step, or it's not just after you flip and multiply. It's like any time you were dividing by something that could be 0, that's a restriction. Any questions? Here's where people would be confused. If you're good at factoring, I think that part's not too bad. People are pretty good at doing that. But then they get to the end and go, do I need to expand that last part? That's where people start to get confused. When do I expand? When do I factor? And when we start adding is when it gets even more complicated. So my advice would be, well, think about, if I expand this, is that going to help me simplify any further? And in this case, absolutely not. If I expand, because you can only simplify in factored form. If I expand it, I'm going to factor it and it's going to look the same. So it's not going to help me. So to me, that's done. I believe the textbook, the back of the book, usually, it doesn't seem to quite always, but almost always expands. But I don't think you need to do that. So it's up to you. Okay, one more where we're adding. Who remembers how you add fractions? Yeah. Very good. Okay, like how would you do it if it was just numbers? What do you need to add fractions? Common denominator. So, and you were describing the process to get a common denominator in a rational expression. It's very good. But in general, how do we add fractions? You need a common denominator. So to get that, the easiest way is to, again, look at everything in factored form. So these are the questions where you factor, and then you do some common denominator stuff, and then you re-expand, and then you refactor. Like, it kind of goes back and forth, and this is where people start to get confused. Okay, so 2 over x plus 3 x plus 1 plus 1 over, what am I missing here? 12. X plus 3, x plus 4. So now I can see what the denominators have in common and what they don't have in common. On the left, I have an x plus 3. On the right, I also have an x plus 3. But what's different are the other two factors, so the x plus 1 and the x plus 4. So I have to add to the left everything from the right that's not already there, and I have to add to the right, not literally add, but like by multiplying, everything from the left that's not already there. So if you want to just watch, so I'm going to start with what I already have, and then what do I have to add? I have to add an x plus 4, and whatever you do to the bottom, you have to do the top, right? So that's 2 times x plus 4, plus 1 over, again, x plus 3, x plus 4, and what's missing so that they don't match? The x plus 1, and whatever I do to the bottom, I have to do the top. Now I have a common denominator. So I can add the tops. The bottoms don't stay the same, but it's all over the bottom. And here's where I will expand and then refactor the top and see if I can continue to simplify. 2x plus 8 plus 1x plus 1 over x plus 3, x plus 1, x plus 4. I don't expand the bottom. That's not going to do anything for me. The top gives me 3x plus 9. Which has a common factor. And then those can divide. So like, why do we do this? Well, that's a much simpler version of what we started with, right? That final line is simplified, sort of easier to work with, easier to graph, let's say, but it has all these restrictions that disappeared. In fact, in some ways, it's easier probably for us as we're learning to just state all restrictions, but this final version shows us that you can't have -1 and -4. Like, it's still contained in that expression. So a lot of people wouldn't actually include those as restrictions. Like, they're still restricted by the nature of this expression. Do you understand what I'm saying? Right? Like, if I sub -1 in there, I get 0, it's undefined. So I don't necessarily need to state that as one of the restrictions, but as we're learning, we do it anyway as a habit. The ones that are the most important are the ones that disappeared. So we have -3 for sure. Any others? I don't think so. X not equal. Okay, what do you think? There's one example, simple, a little bit harder multiplying, and then the harder kind where you're adding. That's a lot. That's a big unit in grade 11, and we kind of reviewed all of it or almost all of it in like 12 minutes. But you got a few days. We're not using this yet today, but it is something that you might need some time to get warmed up on. Okay, so there's a little bit of practice, and like I have worksheets and stuff that I could give you too if you need a bit more practice. If you just want to come in and do a couple together, that'd be a great idea. Everybody good? Okay, let's move on to our actual task for today. And we're going to do, I think, 4 of these. Consider each pair of functions. Are they functions? And complete the following. How can we use one of them to understand the other? And then we're going to graph each of them. What does f at x look like? What kind of a graph is that? Kyle? Yeah, very nice. It's just linear. Nothing fancy about that. What kind of a graph is g at x? Kyle? It's a reciprocal. It's the kind, that you see in grade 11. But you probably didn't talk about it in grade 11 the way that we're going to look at it. And in grade 11, it's kind of like the nasty one, like it's hard to draw. It's hard to do transformations too because all the points are so small and tight and like, it's kind of messy, right? But we're going to take a really different look at it. It's a lot more interesting. So how can we use one to to understand the other? Well, let's graph f at x first. So x minus 2, it has a y-intercept of negative 2, and it has a slope of 1. So there we go. Now, how can we use that to understand g at x? What does reciprocal mean? Like, we call this the reciprocal function, and you talk a little bit about reciprocals and that relationship in grade 11. But what does it mean? Kyle? Okay, careful. It's not an inverse function. I don't know if that's what you're saying. It's a reciprocal function. It's different. What does just the word reciprocal mean? Forget about the function. Just reciprocal. If you take the reciprocal of something, what do you get? Yeah. Yeah. So like if it's 3, you get 1 over 3. You always flip it, right? So it's 1 divided by, but you basically flip the fraction. If it's 2 over 3, you get 3 over 2 if you take the reciprocal. If I take the reciprocal of f at x, x minus 2, I'm taking all those values and I'm flipping them. Right? So if I take the value of f at x here and flip it, it's 0. Like the y value is 0. If I flip it, what do I get? It's undefined, so you can't have that, right? So we have an asymptote there. You know that already, right? I think you probably already know that. So we have an asymptote there, so I'm going to draw it in. Why do we have an asymptote, though? Is like in grade 11, you probably think about it as a transformation, and you know that there's an asymptote in the base function, so then it shifts with the graph. But if you think about how this is a reciprocal of f at x, x minus 2, and x minus 2 equals 0 at that point, the reciprocal of that is undefined. So the reciprocal function can't have a value there, because it'd be like 1 over 0 or whatever. Okay, what else can we know? What is the value here? What's the value of f at x at that point? What's the y value? It's 1. What's the reciprocal of 1? 1. So these two, so f at x gives me 1 there. So its reciprocal is going to be the same, because the reciprocal of 1 is 1. What about here? What's the reciprocal of negative 1? Negative 1, right? It's still negative 1. You flip negative 1, you get negative 1. So same thing. So the reciprocal function has to have the same value at that point. So that means that my function is going to come down, go through that point, and then level off. And why does it level off? We'll talk about that in a second. And same thing, it's going to come up here and go through that point and then level off this way. So we didn't graph that with transformations. We graphed it by thinking about the function that it is a reciprocal of. Does that make sense? Kinda. Okay, so let me talk about a couple of other things. Why is there an asymptote on the x-axis, and another way of thinking about not only where the asymptote is, but for example, does my, like g at x is the red line, does it approach that asymptote from the right or from the left as it increases, as it decreases, like thinking about those properties. So again, look at the blue line. As it goes off to the right, what's its end behavior? What's it doing? It's getting bigger and 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 bigger that way. Is that right? As it goes off this way, it's getting bigger and bigger and bigger and bigger and bigger. What if I take the reciprocal of a really big number? Right? What happens? It becomes really small. So there's my asymptote. But it never gets to like infinity or whatever, so that it'll never hit 0, right? Because again, the reciprocal of that wouldn't make any sense. So as this gets really, really big, it's going to be like a trillion. Then that's f at x. Then g at x is 1 over a trillion, which is really small, but still never 0. So this is going to come down as that goes way out that way. As f at x goes way out to the right and way up, it's going to come down and get really small. And then same thing out here. This goes way down to the negatives. Right? Negative a trillion. Then g at x will be negative 1 over a trillion. So it'll never hit 0, and it'll never cross back into the positives. That doesn't make any sense. And what about this? Well, f at x, as it gets close to 0, gets really, 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 really small before it hits 0. Right? It'll pass through 1 over a trillion. F at x, the blue line, will pass over 1 over a trillion before it hits 0. And the reciprocal of that is a really big number. So that's going to go really, really big into the positives, g at x, as f at x gets really small coming from this side, and then same thing from the other side. So you think about the standard function, let's say, in this case the linear function, think about its behavior. What is it doing? As it approaches 0, as it goes to infinity, where is it passing through? 1 is an important point because the reciprocal of that we know. Where is it passing through negative 1? Where is it passing through 0? Those are the key points. The other thing you can think about is where does it pass through? So where does it pass through the y-axis here at 2? So where will g at x pass through, negative 2, sorry. Where will g at x pass through the y-axis? Negative a half, 1 over 2. Right? You can take any value that you know and just flip it to get a value on the other one. So sometimes it might be the y-intercept, sometimes it might be just any other point that you see as a nice point. You can flip it, and that can give you some ideas about where the reciprocal function is. Does that make sense? So I wonder if we can write some of this down. F at 2 equals 0. Therefore, g at 2 equals 1 over 0. Well, no, but asymptote, right? F at 3 equals 1. Therefore, g at 3 equals 1 over 1, which is 1. F at 1 equals negative 1. Therefore, g at 1 equals 1 over negative 1, which is still negative 1. How can we use one of these graphs to understand the other? But Mr. Belair, what's the point of all this? Because, I mean, yeah, they're not the most fun functions to graph, but in grade 11 you graph them. No big deal. This maybe seems like overkill because I could have just taken the standard graph and shifted it. Well, what if I have to graph something like this? G at x is 1 over x squared minus 4. Whoa. That's not a graph from grade 11. So how do we do that? Well, we're going to do it by thinking about f at x, x squared minus 4, and then the reciprocal, and looking for those key points and what it tells us about our new function g at x. So first of all, I'm going to take f at x and I'm going to do a few things with it. What's one thing that we can do? Factor x plus 2, x minus 2. What does that give us? The x-intercepts, zeros. Very good. What else do I know about this? This is a weird one, x squared minus 4. It's already in vertex form, right? So what is the vertex? 0, negative 4. Does it have a stretch? No, no stretch. No compression. Nothing like that, so let's graph it. There's my x-intercepts. And then 2 more points. So there's f at x. All right, so how do I do g at x? Well, again, look for the zeros. There are going to be asymptotes there. So I'm going to have 2 asymptotes on this graph. What does f at x do as I go way off to the left like that? It gets really, 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 really big. So what will g at x do? Get really, 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 really small. They both have to pass through. Where does f at x equal 1? Right here. So they pass through that point together. They always cross at that point. Oops. Okay, so it's going to cross through that and get really small going that way. And then it's going to approach the asymptote that way. Because f at x, as it approaches 0, its reciprocal gets really, really big. We're going to have a mirror image of that on the other side in this case. It's not necessarily always true, but in this case it certainly is. So I'm going to start up here and come down and pass through that point 1 and then level off. But that's only the 2 outer arms of the graph. What about the parts between the asymptotes? Okay, well, let's look for some key points. So again, I've got where it equals -1 in 2 places. And I can think about the vertex, let's say, for example, is at -4. So what's the reciprocal of that? -1 over 4. So it's going to go through like a point way down here. What about these points? -3, so 1 over -3, 1 over -3. So it's going to be like, and as it gets to 0 on the other side, it's going to get really big. So it's going to come up like this, pass through that point. It flattens out really quickly, kind of looks like that. Whoop. Passes through that point and goes this way. It doesn't look like a parabola in there. It's not a mirror image of a parabola. Don't do that. It looks really flat. And there's g at x. Any questions? Do you think you can do this? Look for all those key points. The asymptotes at the zeros. Look for where it's equal to 1, where it's equal to -1. Think about the end behavior. Yes? Can I just do what? Yeah, that's what I would do. Yeah. Like, we're sketching these things. We want to know in general what they look like. I can't really draw a graph where you can tell the difference between 1/4 and 1/5. You know what I mean? Like my pencil is too thick for that anyway. So I know that it's 1/4, so it's going to be quite small. And then 1/3, so it kind of just gets, now it won't always do that. There are some that don't quite get down that far. And so they don't get really close to the x-axis. They still get pretty close, but they're not like really, really close. So think about that a little. And then, I mean, I wouldn't plot points necessarily, but I would think about how it's -4, so -1/4. And the two other points that you happen to know, sometimes you will, sometimes you won't, that are -3 on both sides, so -1/3 on both sides. Yeah, just think about those points in the reciprocal. Make sense? Okay? Okay, let's try another one. So f at x is x squared plus 6x plus 5, and g at x is 1 over f at x. So it's the reciprocal of f at x. 1 over x squared plus 6x plus 5. What can we do? I can't graph x squared plus 6x plus 5 like that. What is it? What does that tell me about the function? I can factor it, yeah. Okay, so I know the y-intercept, but that's it. Not very helpful. Plot that if you want. But we're going to factor it to see what else we can figure out. So is this x plus 5, x plus 1? What else can I do to learn more about this? Ready?
Sub-random points in.
Yeah, could do that. Yeah. Complete the square, and what will that do? Give me the vertex. So let's do that. How do I complete the square? I'm going to do this the long version in case you haven't. Well, we did it once earlier, but so remember, I take the x squared and the x term, and I like separate them from the rest. And I take half of the coefficient of the x, so half of 6 in this case, and square it. So 3 squared is 9. I add that and subtract that. So I'm effectively adding 0. So I'm not changing the function. Then I take the -1 outside the brackets. If this was a more complex completing the square question, and it had a coefficient on the x squared term, you'd have to do extra work, but this one's simple. And now x squared plus 6x plus 9 is a perfect square trinomial, so this is x plus 3 squared minus 4. So I've got a vertex of -3, -4. -3, -4. Whoops, there. I've got my two zeros of -5 and -1. I've got my y-intercept of 5. Can anybody think of another way I could have found the vertex? Cal? Nice. And how would I find that?
You add -5 and -1, and then you divide by 2.
Yeah, it's right. Yeah, very good. So it's right in between my two zeros. So if I'm looking at that on the graph, that's easy to see. So it's -3, and then I sub -3 in, let's say to f at x. Like I sub it in, get the y value, and there's my vertex, right? Or I could do it here. So -3 plus 5 and -3 plus 1, multiply them together, you get -4. Okay, so let's graph this. So I'm going to have another point over here. 2 points here. Okay, see if you can figure out part of the reciprocal function, g at x, 1 over f at x. Remember to think about those key points. Where is it 1? Where is it -1? It's got to pass through those points. Where are the asymptotes? Any other points you know? This one's going to look quite similar to the last one, but I really, really warn you, don't just draw it the same way every time. Don't just think they're always the same. Don't just say, oh, you know, I already know what these look like. I'll just draw it the same every time. It's not. It doesn't work that way. Okay, so I made sure they crossed at 1 on both sides, made sure they crossed at -1 in 2 places, and then they approached the asymptotes in the same way. Some of the questions ask you to identify the asymptote. So how would I do that? Well, this one has one at x equals -5. And x equals -1. Those are the vertical asymptotes. That's usually what it asks you. It also has a horizontal asymptote at y equals 0, right? So I can identify the vertical asymptotes. I can identify the horizontal asymptotes. Any questions? Okay, one more. What do we know about this function? Absolute value function. It's got a reflection in the x-axis, so it's flipped vertically. It's got a shift, horizontal shift to the right 5, and a vertical shift up 3. So right 5 up 3. No stretch or compression again. So that means the lines just go down at like a slope of 1 and -1. Okay, so what's this guy going to look like? Well, same thing we can draw in our asymptotes at 0. Whoa. And it should cross through the, I missed a little bit, but it should cross through there. Okay. Okay, and what else do I know? Well, I know where they pass through 1. They're going to cross there. I know where they pass through -1. They're going to cross there. It's going to be, the reciprocal is going to be reflected as well, right? Because this part's positive, so it's going to come down, pass through, and it's only going to go to 1/3, so it's not going to go quite as close to the x-axis. And in fact, right here, it should be at 2, right here at, like, or half, I mean, right there at 1/3, because this function is +2 and +3. So it's going to come down and then back up and then cross through. And then same thing here, it's going to approach the asymptote like that. Because f at x is getting very close to 0, so g at x is going to get very, very big. And then going out to the left, f at x is getting very, very big, so g at x will get very, very small. Same thing on the other side. I should be passing through this point, I believe. Any questions?